The stop to think question 2.3 now discussed before brings us to the issue of finding the position from the velocity and also finding the velocity from the acceleration. We do know that we know how to get the velocity from the position. We know that the velocity is the derivative of the position with respect to time, and we do know that the acceleration as a function of time is the derivative of the velocity with respect to time. So given information about the position, we know how to get the information about the velocity of the object, and given the information about the velocity of the object, we know how to get the acceleration. The discussion that follows, it's going to deal with how to go in the opposite direction. That is, given the velocity, how do we find the position of the object as a function of time? And also given the acceleration, how do we find the velocity of the object? So to solve these questions, let's start with the simplest case. So the simplest case is the constant velocity motion. And for constant velocity, so remember that the constant velocity, the position versus time plot looks like this. So the slope of that plot is taken as, you can calculate it as delta x over delta t, where delta x is some defined over between 2 points. Here some initial and some final point. This is your delta x and this is delta t. So from this equation we know that delta x is equal to v times delta t. So if I know the velocity at which the object is moving, assuming that the velocity is constant, if I multiply the velocity by some interval of time, I know how much distance the object covered during that amount of time, delta t. So basically, if I have a plot of the velocity as a function of time, and the velocity of the object in some interval of time happens to be constant, right, that is certain value v, then over that interval of time, delta t, so delta t is this interval of time, over that interval of time I know that the object moved through a distance delta x. Delta x is v times delta t. So what is that telling you is that in a plot of velocity versus time, if the velocity happened to be constant over a certain interval of time, then over that interval of time the distance traveled by the object will be equal to the area under the plot velocity versus time. So let's see if we can generalize this result. Suppose now that the motion of the object is slightly more complicated than constant velocity, but we can still decompose the motion, or the motion is still made up of several segments where the velocity is constant. So let's assume that the object, this is position, again this is time, that the object starts with some initial position over here, that it moves with constant velocity, so that means that's a straight line, over a certain amount of time. It's assumed that the amount of time is going to be delta t for all the segments that I'm going to draw. So the next motion, part of the motion, the object changes velocity very quickly, and now it moves with a different velocity, but that velocity is kept constant over these intervals delta t. So this is delta t from here, this is also delta t, and so forth. See that this is delta t also. So if that is the case, let's see what we can say about the total displacement of the object. So the initial position was here, the final position is here, and the total change in position of the object I'm going to call it delta x. Again, every segment here is a straight line, which means that the velocity is constant over each one of those segments. So if I do a plot of the velocity as a function of time, then for the first segment the velocity will have a certain value. Say that it has this value, constant. Let's call that v1. Then for the next segment the velocity has a different value, seems to be higher, the slope is bigger. Let's call that value v2. Then for the next segment the velocity is also constant, and say that it has a value v3 and v3 over here. So since in every segment the velocity is constant, we know that the change in position of the object over this interval, right, the area of that, if we call it delta x1, is simply the area of that rectangle, which is v1 times delta t. Similarly, for the second segment, the object was moving now with a different velocity, v2, and the distance or the position of the object changed by an amount delta x2 equals v2 times delta t. And finally, for the third segment, the area of that is delta x3, which will be equal to v3 times delta t. And we could have, of course, many more segments. So what's the total change in position of the object between the initial and the final location? Well, it's obviously the sum of delta x1 plus delta x2 plus delta x3. In this plot you can see that those different displacements are, this will be from here to here, that is delta x1, delta x2 is here, the change in position between this instant of time over here and this one over here, and delta x3 is this one. So delta x, which is the total change in position of the object, is made of the sum of the change in position in the first interval plus the change in position in the second interval plus the change in position during the third interval. And if you had more segments, which you could have, then you will just continue to add that. And since in every segment the motion was constant velocity, we can express this delta x1 as v1 delta t plus v2 delta t plus v3 delta t, and so on.